You're right. Great. And but it's always good that some people find the room that I did not explicitly point in the right direction. So. Slideshow from current slide. This. As I suspect slash hope that some people will still show up. Let's wait a few more minutes. Yeah, see? Hi, no, crypto?
Yes.
No, not here.
Okay.
I learn quick. It's a face I really don't recognize. It's somebody, I have to be somewhere else.
Did you see the room for then?
I have no idea. I mean, I booked, well, I tried to book 005 for the entire semester, but yeah. No, this week with Thursday being a holiday, and then all of a sudden, I mean, so Friday would have been an option, but Friday I'm going to be in Portugal. So, and I've never done a lecture while I'm like in a very sunny, like on the, I'm not sure, I'm not a beach person, but theoretically I could be lecturing from the beach. Maybe the lectures become, well, better, maybe it become worse. I don't know. Maybe you should try it once. Yeah.
Do you get over the bad news Thursday?
Yeah.
Still have to grade your assignment on it.
No, it's really like I wrote my bachelor thesis like in this setup,
Okay,
so
yeah.
I also like emotional attachment. So
Yeah. No. It's yes.
yeah.
Yes. But I'm still pissed off and whatnot, and it's sad, and
Yeah.
so much time went in this whole excellence cluster thing. Not just this one, also other attempts. But well, life goes on, right? It's not about the destination, it's about the journey, right? It's about the friends that you make along the journey. And those friendships hopefully will last for a long time and may let them be fruitful. So that is my my opinion right now. No, in fact, I think we should just, well, pick ourselves up, dust ourselves off, get going as quickly as possible, and then perhaps not asking for millions and millions and millions, but perhaps slice it slightly more compactly. Good.
Next possibility now in 7 years.
Yes. For this excellent cluster, yes. 7 years. That is really that. This is one of the most frustrating things. Also one thing that I'm not going to do, but if you were to calculate the, let's say the pure working time, it really was already at the point at one moment while we were writing this one that I know that we were asking, like, even if we as a consortium get the money, was this economically smart decision, or should we just have said, okay, let's just do what we do? No. But like I said, it's the journey, it's not the destination, and I do mean that. Good. Perhaps we talk more about attempts to greatness and then seeing where you strand, right? Let's pick up where we were, because now 3 minutes passed, and I have plenty to say, as usual. Let's see where we, how far we get. Because what I have to say, what I do enjoy, is that if you're looking for crypto, this is the wrong room. If you're looking for TADA, this is the right room. Okay, good. I do enjoy that in the first Causal lecture, I already lectured some stuff that I had planned for the second one, and then it sort of carries over. And I have to say that the story in my head makes much more sense this way. It's just that I never managed to squish so much in. So I don't know if it's you, if it's me, or, well, we will see. We will see. Good. Today is Monday, May 26th. third lecture, causality. Let's get going. As you remember, the question of the 3-4 weeks, what is causation? How can we measure it? How can we discover it? And we kind of covered all three already a little bit. So what is causation was done a bit more than 2 weeks ago. How can we measure it? This is what we touched upon in the last lecture at the end, right? The ANMs, the additive noise models. And how can we discover it? That was the main topic of last week's lecture. So we're going to continue a little bit into the how can we measure it? How can we identify for individual pairs of variables, are they causally related? Or more specifically, in which direction are they causally related? So this is a very quick recap of what we did last week, right? I'm not going to rediscuss ANMs. That would be really a waste of time. But hopefully you do remember that using, for example, conditional independence tests or the score-based methods like GUESS, we can find the causal skeleton. Then we have these orientation rules, again, conditional independence based, where we know that, for example, a collider can only happen, basically these two are independent, but if you condition on a common child, then these become conditionally dependent. Okay, that's one unique situation. We can identify the direction. Then we still have a whole bunch of edges we can't direct with just the assumptions we had so far. Now, maybe I should have interspersed here the ladder of causation slide once again, because up till here, let me go one slide back, up till here is everything is non-parametric. I'm not certain if I said so literally in the lecture, but it is. It's non-parametric. It doesn't matter which functional model is behind it, right? As long as it fulfills these three basic assumptions, four if we take in the IID, right? So causal sufficiency, causal faithfulness, and the causal Markov condition, non-parametric. Doesn't matter what the functional shape, what the noise is, what not, right? Last week I asked, okay, do we want to look into some failure cases? And only Magnus raised his hands, right? I mean, not hands. He was not that enthusiastic. So we can still break those assumptions relatively easily, but otherwise it's non-parametric. Now, the moment we start to make parametric assumptions, of course, this limits us in the general applicability, right? But at the same time, it allows us to identify these directions, as we've already seen last week, ANMs, right? So we have a function and we have some noise that is additive, not integrated. One other thing that I just want to hint already at, in a way, we now are moving with these assumptions from the first rung to the second rung. But by making these parametric assumptions, we are kind of at rung 2.5, perhaps 3. So in the sense that if the true model is indeed following an ANM, then, well, we get not just the causal graph, we actually get the whole SCM. We get the structural causal model. We get the functions. And that is the necessary ingredient for the counterfactual level. Plus some minor details I swipe under the carpet right now, like being able to abduct the noise and blah, blah, stuff like this. But that's not so important right now. But I'm just showing that by now making additional assumptions, we are still interested just in the second rung, trying to find out the causal network. But in order to do so, we make assumptions that are almost sufficient for the third rung. What is the key insight? We played this game. Well, Max already knew it because of a previous lecture, of which you will see some other hints. In that, the key idea being that the noise in the one direction is independent and the other it's not. Right. So the flat areas here, fine. That's where we can identify the direction. That's that. So, and it's strange, right? It would be strange. That is the gut feeling here. That these densities of y and the noise, that they correlate. If you're willing to accept that they correlate, okay, then we can't tell if x or y is the noise or is the cause. Otherwise, we can. So, core principle, as it's been defined a few years later, 2015, was the first time it was semi-formulated. It was further formulated later on. Independence of input and mechanism. So one of the examples behind this, I like it, is suppose that we have a solar panel, right? The solar panel, absorbs photons and spits out electricity, right? Or some voltage, and what you do with it, that's that. Now, that is effectively the mechanism, right? If we now give it fewer or more photons by aiming it more at the sun, or away from the sun, or holding our hand in front of it, that of course affects the output, right? So it does affect Y, but it does not affect P of y given x. That mechanism remains the same. That is the key insight, right? So effectively, there is a true function. This true function stays the same for whatever input we give it, right? And of course, the function may choose to be more effective for lower inputs than for higher inputs, right? We allow some slack there, but the key idea is it's not that all of a sudden the solar panel starts to behave wildly differently if we just turn it ever so slightly, right? That all of a sudden it starts to absorb energy like from the electricity net, right? I mean, that or starts to, I don't know, do a little funky dance. No, that it stays constant. That is the key idea here. Remember that in the first causality lecture, we had this intuition, or at least, I mean, I said that I had it, and we didn't really discuss it, but that somehow P of x times P of y given x, if x causes y, should somehow be better, somehow be qualitatively different from the factorization in the other direction, right? We know from probability theory that it's not true, right? Just by the probabilities, but somehow it should have something different. Now, the key idea from what we have here, right, this independence of input and mechanism, is that in the true direction, we have just some source distribution, amount of sunlight, right, or maybe the orientation of the solar panel. And then, well, the solar panel itself, that remains the same. P of y given x remains the same shape, no matter what x we put into it, right? That is constant. So in this direction, we have a simple distribution here and a simple constant distribution there. In the opposite direction, we don't. This is the same thing as this insight that we had here, but you can, of course, model it from y to x, but all of a sudden, this shape, right, this function and the noise, they start to correlate. So somehow this here, P of y and P of x given y, they need to know about each other. And if they don't know about each other, we somehow otherwise need to inform. So there is information about P of y still here in P of x given y. And it shouldn't, because that makes these mechanisms dependent. So last week, we looked into literally measuring these independences, right? And if we can find in one direction, we can make it independent, in the other direction, we cannot. Aha, A&M, under the assumption of an A&M. This assumption here is slightly different and in the end way more powerful, because now we're basically in general saying simpler. Huh? So if this one is somehow simpler than that one, by terms of what mechanism do we need, how flexible does this mechanism need to be to fit the data, we point out what is the causal direction just by finding that direction that is simplest. Raising the question, how can we measure simplicity? I'm going to shut up Max for a second and then he can give the answer. But what do the others say? How can we measure the simplicity of the one or of the other? Any idea? Because we have already seen it, the key idea. And everything is connected to that. Marcus?
I mean, it's as simple, so it might connect to information theory and to MDL somehow.
Mm-hmm. Yes.
Like, yeah, think about distributions, like simple, like I think the most complex distribution is like if it's 50-50, like at least for one bit. And this might relate to simplicity.
Yeah, that is the intuition. I mean, we will need to sharpen it a little bit before we can formalize it, but indeed, that's the intuition. That's also the intuition that I had back around 2011, something like this, that the causal model somehow should be simpler. And well, I like MDL, I like information theory, so okay, we should be able to point out causality using compression. I was not completely, well, I didn't work out all the details just yet. But Dominic Jansing, well, and et al. Is just mean hiding Bernard Schulkopf in this particular case. They had worked out those details already, and that this paper was already under submission since 2010. And yeah, they figured out under which conditions we can actually do this. They have a postulate that, well, goes from the Markov condition Markov condition we know, we have a joint distribution and we can factorize it such for every variable. We just need its parents. We don't need any additional, we don't need its children. We don't need any other causally unconnected variables, right? I mean, we can factorize it as such. But the problem here is, sure, you can have parents, but I mean, there's different possible factorizations. How can we now choose which is the simpler one? Because I can factorize x and y in the one direction or in the other direction, right? Both are valid Markov condition factorizations. That's exactly why the Markov condition gives you a Markov equivalence class, where these two are connected, but nothing else. So how can we go to simple? You mentioned MDL. MDL is perhaps one step too far, because MDL, we need to instantiate Kolmogorov complexity, which we saw in bird's eye flight very quickly, right? I asked what is a Turing machine and whatnot. And if we plug this around, then all of a sudden it starts to make sense. So this is the complexity of the full joint distribution, right? And now what is that going to lead to? Well, that is going to be a sum of each of the Kolmogorov complexities of the distributions, not really of the distribution, not of the variable, given its parents. The key idea being that if indeed we have this solar panel, that is one mechanism, that is one program, right? You just have to program, okay, this is how a solar panel works, and well, then it gets some input. This input also needs to be described. You have to write some program that specifies the input. If this is completely random, okay, well, then this will have to be encoded verbatim. If there is some structure, good for you, you can squeeze out this structure, but that is going to be the shortest description of this system. In the opposite direction, it's going to be more complicated. Think again of the example I just gave, where P of y and P of x given y, they correlate. This means that you first have to describe P of y, and then your mechanism, the P of x given y, needs to have a, if the input from y is this, then I'm going to do that, and otherwise I'm going to do such, and otherwise I'm going to do so. It's going to be a much more complicated program. This gives you a unique factorization. Unless the process is deterministic, then you're screwed. If it's deterministic, then you can, well, then the function is invertible, but that kind of goes hand in hand. Then you can write your function from left to right, right to left, and there is no difference, right? But as long as there is some noise in the process, the algorithmic Markov condition, or AMC, is your friend. Now, what Dominic and Bernard postulated, because we can't prove it, but the Kolmogorov is the factorization of the full joint such that the Kolmogorov complexity of that factorization witnesses is the same as Kolmogorov complexity of the full joint. That corresponds to the true generating process. Effectively, they're saying, well, not so much nature is lazy, but if we're really in the limit, right, because we're really reasoning about distributions here, we're really in the limit, then there is no reason why it should be the more complicated one. It does not fit, and they have a whole list of examples, essentially physics, right? I mean, entropy going up rather than down, unless you infuse energy. Energy has to come from somewhere, and so on and so forth. There you are. Now, the problem is a little bit, we can't prove it. I mean, we can't even compute Kolmogorov complexity, right? So also the proving is kind of difficult. We also remember that it's subject to the Turing machine, so your favorite programming language that's under the hood, right? If Max likes Python and you like C# for whatever reason, right? Then the actual shortest programs that you guys can write are going to differ a little bit, right? And in the limit, it doesn't matter because you can do this cross compilation game. But for shortest, so just as the definition, because previously we were thinking about how we can do this for patterns and whatnot, right? Relatively easy. What is the Kolmogorov complexity of a distribution? Well, it's always the shortest, the length of the shortest program measured in bits to compute the object at hand. And for a distribution, Kolmogorov complexity is defined as such. So we're looking for what the length of a program, that's just a binary string. We feed the program to a universal Turing machine. We give it a certain input and, well, a particular precision Q that we want to compute. And then we compare the output of our universal Turing machine, of our program, to the actual probability. And what we want that the difference between the two to be smaller as 1 over Q. So Q is really a precision, right? But, and you can make Q arbitrarily small, right? And that, so there are some questions of like, okay, do you get different Kolmogorov complexities for different Qs and whatnot? For us, this doesn't matter because we're reasoning in the limit. We set Q to basically the smallest possible value, just not 0, and so on and so forth, right? We can approximate arbitrarily closely. You might say, okay, it's still an approximation. And it's okay, yes, you're right. But at the same time, I do not believe in distributions. I believe in processes. Processes you can turn into a program, right? I mean, not so effectively. I really believe we live in a giant Turing machine. I don't believe that we live in a giant die.
Professor?
So P star is then the shortest program, the best compression of this distribution. If we have a uniform distribution, of course, we need to specify this over some interval, then, well, what is the Kolmogorov complexity of this? Just intuitively. Low, high, respectively, what are the things we will need to encode? Max, you may speak again.
I mean, because it's always the same probability, it's quite simple.
It's a very simple. So what is the necessary information that you need to put into your program, into this P star, in order to be able to, well, get your uniform distribution?
Just the interval, basically.
Just the interval, exactly. So basically 2 numbers, right? I mean, up to some precision, and that's that, right? But, so yeah, this is simple. It's constant, right? We have here, this is, I think, a Gaussian. Maybe it's a T distribution, I don't know. I mean, that, Gaussian with high variance, have a high variance. What is the Kolmogorov complexity? Elina? So the core question, just like the previous, is with intervals, is like, what are the key ingredients? What is the core information that you will need to, well, model what you're seeing here? Yeah. Yeah. So okay, but you can imagine that in this case it continues. Otherwise, we can also cut it off, then we just steal Max's answer. But we need to make sure that within this interval, right, or this infinite interval, that it takes this shape. What do you need to encode a Gaussian? Mean and variance, exactly. So we just need to say, okay, which value is this and how wide is that? And then you can slap indeed an interval on top of it, but it's again 2 numbers, right? And the moment that we've encoded these 2 numbers, the program itself to the shape of a Gaussian, I mean, I also always have to look up what it now is exactly because it involves pi and whatnot, but in the end, this is straightforward, right? So also constant. This is my depiction of a random sample or random process. How many bits, or how would you encode this? You have to speak up a little bit, otherwise I can't hear you.
Maybe it's the data itself.
The data itself, yes, exactly. Because if it's truly random, there's no structure. So yeah, so this will be a lot of bits. Those 2 are, well, basically no bits, right? So this is basically the intuition that we want to go after. So, I could have done a lot of things in between all 3, right? But in general, the more complicated distribution, that's exactly what Kolmogorov picks up, right? So the easier it is to squish it into a program, there you are. Now, if we take this algorithmic Markov condition and we ignore the entire sum, right? And we just look at 2 variables, then effectively what we get is that if x causes y, this factorization, so the Kolmogorov complexity of the marginal of x and of the conditional of y given x, is going to be smaller or equal, equality again if it's deterministic, to the opposite anti-causal direction. I have here in gray, and in this projector you can actually see it, because I also made it almost dark here, it's very cozy, up to an additive constant. Kolmogorov complexity, this is the difference between your favorite programming language and somebody else's. In the limit, it doesn't matter, right? It's an additive constant, so it doesn't matter in the determination, is left better or right better. So this is the idea that also Jansinger Shirkov postulated, that we could hopefully be using this to tell cause from effect. Now, one of the assignments is to study this program, so I'm not going to give away too much. But let's say an open question is, how practical is their framework? And how far ahead did they look? But intuitively, what it says is that it's easier to describe the joint distribution from effect to cause than anti-causal direction. Practical issues, homograph complexity is not computable, and we also don't know the true distributions. We also need to somehow get those, right? The not computability, we can already solve. We saw this in the pattern mining lecture, right? I mean, Magnus already gave the answer, using MDL. MDL is, well, the statistically sound approximation of homograph complexity, where if we allow the model class to be all programs, it is exactly going to be the same as homograph, and we have the same computability issues. And if we shrink it, then we have a chance at actually computing it. But of course, if the true program lays outside of the model class, it may be arbitrarily bad, right? Their outcome. So this is a bit of the, it makes everything a little bit more exciting. Good. Now, what we, and we as Alexander Marx and myself, actually not in 2017, was it? Now, formally we showed it a few years later, but that doesn't really matter. We showed that basically by replacing the K's with an L, the L for description length for MDL, and the P of X and the P of Y given X, swiping this also into the encoding, because, well, we don't have these distributions. We will estimate them on the fly, right? But then we arrive at a simple formula that looks like this, where again, we're just measuring bits, but now subject to our encoding. And back in 2017, we had the idea of like, well, if we focus on continuous value data, can't we use regression? And can't we then effectively use regression errors? So the better your regressor is, the smaller the errors are, the fewer bits I need to send. So we need an encoding of how many bits do I need to send for a certain amount of error. That's the one idea. And the other is that, well, if you need, like, if it's true that in the causal direction, life is going to be simpler, then probably you also need a simpler function. Let's say a polynomial of a lower degree than in the anti-causal direction. And specifically, if we now combine these two ideas, that maybe in the anti-causal direction, you can't find shit, because it's like, what is this even? So you choose a very simple function, but with a very big error. Hey, MDL allows us to measure both in bits, and just say, this takes a shit ton of bits, this takes very few bits, I go for few bits, right? So we're not plainly going to go for the complexity of the function causal, anti-causal. We're not plainly going to go for regression error, causal, anti-causal, but we combine those. That is the core idea. How do we encode things? The marginals, so the light blue boxes, we use a Gaussian point model. Basically, we assume that those are Gaussian, and we just fix a mean and variance, right? Based on the data, we fit it. And what is then the number of bits? Well, you get a certain probability for each data point. You remember perhaps from the pattern mining lecture that by just taking the negative logarithm to base 2 of a probability, that's the number of bits that we need to transmit something. Okay, done. You can argue, and in a way you should immediately argue, like, wait a second, Gaussian point model, are you now really assuming that X and Y are Gaussian, and what if they're not? Fair point. I'm just going to say shrug, because we need to do something, right? It was 2017, we were young, we were stupid, we needed the money. This was the first paper in its line, right? But you can definitely argue that using a Gaussian point model there, rather than, I don't know, using a kernel density estimate or a Gaussian process or whatnot, we could have done a million different things that might have been much better, but hey, let's get started. Then for the conditionals, this is why I already spoiled the idea, regression. If we just regress X onto Y, then effectively, well, we get errors that we aim for zero mean. You want to have as low as possible variance. This is what your regressor tries to do, right? And these regression errors, we again model like a Gaussian, just like we did over here, right? So this is basically the noises, noise for Y, noise for X, right? We treat them as if it's a Gaussian, we encode them as such. This also shows immediately why we chose a Gaussian point model here, because effectively we just have a, well, let's call it a flat regressor, right? For X, we just take the mean and then, well, whatever the variance, that is basically regressing X onto, well, onto nothing. Okay, good. So that allows us to measure these errors in the same, let's say, same way, the same range and everything. Also allows us then to relatively easily add those bits together. The only thing we still need is to measure somehow the complexity of these functions, right? F hat and G hat respectively. Because if we ignore that, then yeah, it might be that in the anti-causal direction we have a super simple function, in the causal direction we have a super complicated one, and then it can go arbitrarily wrong. Yeah, effectively what we do is that we expect the world to look like this. So y is just a function of x, and then some noise, which is independent, right? Like we assume in a regression. And as f, we looked at it parametrically. So we looked specifically at a function class that included linear, quadratic, cubic, exponential, reciprocal functions of those. That was the first set of functions. In a later paper, we expanded even to a larger class of functions. And effectively what we do is to encode this. How many bits does this take? First, you need to know, right? This is again the game, like what is the necessary information? So if these are the 1, 2, 3, 4, let's ignore reciprocal for now. These are the 4 possible, let's say, subclasses of my model class. I need to transmit to you first, which am I going to use, right? So I can do this with a fixed block code. So 1, 2, 3, 4, a logarithm to base 2 of 4, right? I only need 2 bits to transmit which is it, right? Okay, it's going to be a cubic function. Now you know it's going to be cubic. You don't know the parameters yet, but you do know, by knowing that it's a cubic function, how many parameters we need to encode. Okay, we encode parameters up to a certain precision under some baseline model, meaning that the moment that you know that it's cubic, you know how many parameters to expect, you can just read off the bits from the bit stream, you can reconstruct the parameters, and you can get the shape of the function back. This example here, well, obviously this is cubic, right? If you were to fit this with a quadratic function, you're not going to have a good time, right? I mean, maybe this part you could get, but here it's going to be wildly off, right? If you use linear, well, linear is going to be better than quadratic, right? But of course, you're not going to have a great time there either, right? That's good. So that is the general idea. How well does this work, right? So this was the first. Well, technically, it was basically, I think, the first project of Alexander's PhD, or Alex. Never called him Alexander, I think. Yes. Oh, that. I'm sorry. Thank you for saying that. Okay, I didn't realize. Okay, sorry, online. Somehow Zoom didn't notify me. Good. I don't know why Zoom did what it did, but okay. Good. Can't do much about that. Right now, I can't see at least. How well does it work? Well, like I said, this was the first project by Alex. And this was the plot that he came back with. Let me walk you through it. What are we reading here, right? And why was I more than a little bit skeptical? So first of all, it's a decision rate plot. So here's decision rate. What is a decision rate? A decision rate is that in this benchmark, right, you have to make lots of decisions, basically classifications. Is it X to Y? Is it Y to X for all sorts of different data sets? And I allow you to order these decisions from most confident to least confident. So imagine that you're writing an exam, right, and you're allowed to order the exam questions, right? 1A, 7B, and so on, in that order where you think, okay, well, here I'm most certain I'm correct, right? And then I start grading, and after, let's say, half an hour of grading, I need to stop. Something like, or 10 minutes. So it's to your benefit to put your best answers up front, right? And the ones where you really don't know, you can think of it like that, right? Or somehow I weigh the questions that you really put at the end, I weigh them a bit less. It's also how you can see it, right? But good. Now, these are yes/no questions, X, Y. So what we what we can also do, we can also see what's going to be the effect if we just flip a coin, right? And how often are you going to be correct? This is what this gray envelope shows. This is the 95% confidence interval of a coin flip, fair coin. So any line within this gray envelope is as good as a random coin flip. This is like 10 years of research, these numbers there, or the lines. So this, and what we then have on the y-axis is the percentage of correct decisions over the top 1, top 2, top 3, top 80%, and so on and so forth, right? So you can really see what is the performance of a method from when is it really confident to when is it less confident, right? Really over the top game. Effectively, you can also imagine it that I can put a threshold to, well, either a percentage of the decision rate, or I allow you to say, well, you know what, up till these exam questions, I'm quite confident. For the others, okay, no, right? I mean, don't trust my answer. Well, for exams, I still have to grade everything. But suppose that you're a medical doctor, right? And somebody comes in like, okay, I'm really certain this person has a broken leg, right? I mean, let's operate or do what we... And this person, I have no idea. Then I would like it if you would say so, that we don't start operating or amputating somebody's leg, right? Who actually had just a splinter in their finger, right? And that's so confidence is important. The purple line at the top is what we just saw. Just doing regression with then, well, effectively counting parameters and encoding them in a smart way. And it kind of obliterates A&M, this is the yellow line that we saw last week, right? That goes up to here in the gray envelope. Then residual, this is residual independence test. It's where it's the idea of an A&M, but effectively what we do, we regress, but we try to maximize independence, and then we just take the direction that maximized, but with the larger independence. As you can see, the blue line, is really at the very end, where basically say, okay, I don't really know, right? Where it starts to beat the coin flip. So do you want to put your life in the hands of not really, especially if you see how bad it is at the beginning. So Alex showed me this plot, and I was like, okay, well, show me your code. Because it's not that I don't trust you, but if we really have such a big gap, then either everybody is stupid and we are incredibly smart, or we're doing something wrong or strange. Well, was correct. For this benchmark, right? This is roughly 100 cause-effect pairs. This approach works wonders. However, then came Natasha Tagasowska from Lausanne. She was very inspired by our work, and she looked at a larger class of benchmark datasets. So let this be a lesson. Don't trust one single benchmark, right? Don't trust ImageNet or whatnot. Look broader. And what we can see here, so this is a radar plot, the dashed line, these are our scores. And on the 2 being 1, well, we're very close to the edge. Edge is good, right? So we perform really well. But you can also see that for LS, for example, location scaling based noise, not so great, right? That's this is multiplicative noise, not so great. Basically, she managed to conjure up the benchmark from hell for our method. She didn't do this on purpose to tackle us, but she and her advisor thought about, okay, what are the classes of things that we should be able to detect, and how would it work? And then, so it turns out Alex and me came up with a method that works like shit on theory, but really good in practice, because that is the only practical benchmark, which should make you scratch your head. What is actually going on? Right? Maybe the benchmark is too simple. One other thing, slope, this is called because regression slope, does it come with any guarantees? No, none. It's based on this AMC idea, right? It's a postulate. We can't give cold hard guarantees from it, so no. But we were sad, right? We were first very happy, then we were sad. Then in 2018, Patrick Bleubaum and others came up with an idea of, well, effectively building on our success, but then looking a bit more into the theory side. And they came up with, well, if we look at the expected regression error from cause to effect and effect to cause, then we can put conditions onto that. And in the specific conditions, we can actually tell cause from effect. I'm not going to go through all the details because, well, it's quite a hairy paper, but effectively what they do is that they assume a causal model like this, where alpha goes to 0. It's not 0, but it's low. So, and this is the weird answer. If it's 0, then all of a sudden everything becomes non-identifiable. But the moment that it is too large, then you may not be able to find the correct function. And it's very difficult to tell what is the correct function for the data you're looking at. But if alpha is small, you can do that. Now, if the noise is unbiased, well, that makes sense. Noise needs to be 0 mean, right? I mean, otherwise the function changes. Unit variance, that is just a convenience from the math side. X and Y need to have compact support, meaning that you don't want to have a completely spread out distribution. You want to have something that you can really reason about, not too fancy shapes and whatnot. And the function, well, non-linear and twice differentiable. Twice differentiable is what you need for the expectation calculations, otherwise you're dead. And the nonlinearity, well, nonlinearity, given that we have the unbiased unit variance noise, otherwise we land into the A&M trap that we saw last week, right? So in a way, this is an A&M on steroids, but they look here specifically just at the regression error, right? So the true Y versus how we can model it, and in the opposite direction. And in the true direction, then we're going to have a lower error sense. This is assuming we know the true function class, f, which, well, in practice we don't. And you note that compared to our setup, there is no regularization for this complexity of f, respectively g. So in that sense, Reki, regression error-based causal inference, is fantastic because we have guarantees. However, in practice, yeah, you need an oracle to tell you what you're actually looking at, and that is exactly the problem that you want to solve. So, effectively, what we can look into, or what we will run into, is that essentially what we have here. Number of parameters, so you can read this as degree of freedom, right? If we use a spline or anything in neural network. And this is the score, let's say the regression error, right? And in the causal direction, you see the black line, this very rapidly drops down and then hovers around this dashed line. The dashed line is the theoretical optimum, but given that we have a limited sample, then there you are. The red line is the anti-causal direction. And as you can see, it also goes to exactly the same point, because we still have, thanks to probability theory from statistics, well, P of Y given X, P of X given Y, they're marginals done, right? So it is only natural that they arrive at the same. So the intuition, however, is and remains that the anti-causal function is not simpler, right? Typically, it's going to be more difficult, but it's not simpler than the causal one. And if we now use regularized regression, then we get this plot. Basically, we penalize with a number of parameters. So, of course, if you get a better fit, great. But then if you get more parameters than you really need, it doesn't outweigh the benefit. So it starts to come up. Now we have a clear minimum that we can say, like, the black line here wins, it beats the red line. And this means that, well, X causes Y rather than Y causes X. This is where we want to go. This is the intuition. Now, I'm going to just very quickly show the basics of this. We didn't even get to discuss it in detail so much in the seminar, but there it is. Kolmogorov complexity. So basically, the last, you could say, stroke of genius by Kolmogorov was to look at Kolmogorov complexity as a means to do model selection, to determine what is the best model for the data. This may sound like an easy, trivial question, right? Especially given that you've been a bit indoctrinated from an MDL perspective, but also previously from a regularization perspective, L1, L2, whatever loss, right? I mean, that gives you a unique or unique enough solution. Is that is that the best explanation for your data? Or are there equivalently good explanations for your data? It's a bit of a philosophical question. And what we have here is Kolmogorov's structure function. I'm going to walk you through it. So we have some data X, right? So this is our string. We could make this the distribution, right? But we stay at a very high level. Now, what is going to be the structure of the data X? Well, I'm going to give you a budget alpha. And alpha is the number of bits that you're allowed to use to describe the true structure of X. So it's an upper bound on the length of P star between quotes, right? That you're allowed to use. So we have here K of S smaller or equal than alpha, right? Suppose that I set alpha to 0. Well, obviously you can't even spit out a program, right? I mean, of length 0, right? I mean, there's nothing of homograph length 0. Is this thing still defined? Yes, because what we're looking at, what is the function of h of x? It's the minimum s, where we look at the logarithmic size of s, and s is a set that includes binary strings, and it needs to, at the very least, include the data itself. So it is, in a way, the smallest set S, what we're looking at, that includes our data. Now, the moment that I allow you not 0 bits to essentially define S, that's what we're doing here, but I allow you 1 bit, 10 bits, 100 bits. If I allow you infinitely many bits, if I set alpha to infinity, right, I allow you everything, what are you going to do? Then you're going to go for S, this becomes the singleton set with just X. Because choosing X from this set, this is why we have this logarithm, is that the cheapest, right? That it doesn't cost anything, it's just one object. This allows us to separate the structure in X by defining these sets S from the noise in X. So what we now get is here in this plot. On the y-axis, we have, well, the cost of finding X in set S. And, well, it starts here at Kolmogorov complexity of X, right? This is basically where things get interesting. On the y-axis, I have alpha, right? So this is the budget, which stops to be interesting at complexity. I can give you an infinitely sized budget, but any budget above K of X, well, you're just going to use the Kolmogorov complexity of X, that's that, right? You don't need anything more. This line is called the sufficiency line. So this is the best way to describe this data. But what is now interesting is that you see that this h of x, it sort of bumps, bonk, 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 up onto and then away again from the sufficiency line. And we can analyze this behavior because here you have too little budget to define any meaningful S, right? Any meaningful set or model for your data. And only here it starts to become better, right? But not quite good. And here I give you a budget such that you can craft a set S for which X is a completely ordinary member. All the noise, right? So S is basically a collection of friends of X, so to speak, and you can't really tell them apart. The noise is uniform. That's how you can think of it. Hence, this index works. But alpha 0 is then the smallest program that creates an S, such that if we separate the complexity of the set and the complexity of pointing out X in the set, then we are at Kolmogorov complexity. This is the minimal sufficient statistic. Right now, with this alpha, we have picked up exactly, like in the examples, the interval range, or the mean and the variance. It's just that information, nothing more. It's the minimal sufficient statistic for this particular data. Does that mean that there are more complicated models that might give you a bit more insight? Yes. There also are other points where alpha witnesses the Kolmogorov complexity or the sufficiency line. Now, this first bump, this is what we then will show, or show in the paper. This first bump is where the causal direction hits. These other bumps, this is where the anti-causal direction sort of hits. In other words, in the causal direction, alpha 0 is lower than in the anti-causal direction. We can separate out more noise because it's inherently more independent. And the key thing about this, I mean, if there's anything that you want to take away from this complicated slide, the concept of sufficient statistics, hopefully you know, but the concept of being able to choose which sufficient statistic is minimal, which is the least complicated. You need the least effort. Kolmogorov complexity allows you to identify this. There's no other, well, at least there was no other way known. Maybe in the meanwhile, there's other angles at it, but by an algorithmic framework, you can point out this is the simplest really way to describe this data. And good. Building on that, now we go back a bit into reality. I, to me, thought, okay, well, let's build in a simplicity assumption. It follows, real world follows this Kolmogorov structure function. So let f be the true function from x to y, and well, we will allow an inverse mapping. Otherwise, if there's no mapping, then yeah, obviously in the one direction, things are going to be much simpler than in the other, or the errors, right? So let's keep things a bit exciting. So let there be inverse g. Then this is the assumption that we take. The L0 is really simply just counting parameters in this particular case of the true function should be lower or equal than the anti-causal one. Follows directly from the regularization bumps, right, that I showed before, and Kolmogorov structure function. Effectively, we say that the causal process is at most as complex as the anti-causal one, and if it's as complex, then we hope that the regression error kicks in. If you have linearly independent basis functions, hello EML, this holds. It will, in the anti-causal direction, you will need more basis functions, you will need more parameters. If you have a polynomial of degree k, yes, you can invert it, but it will be at most as complex as the anti-causal direction. Typically, you need more. And in general, if you just look at how difficult is it to learn a mechanism from x to y, y to x, you will often see that if you learn in the anti-causal direction, your model will either arrive at a worse error, or it is more difficult in the sense that it will need more epochs, more training in order to arrive at a similarly good model. So there is something to be said here, but these are not cold hard evidences. Good. So how do we now put this to practice? We start from Reki here, and we change it to this. Well, basically this thing we just called error x to y, and this thing we called error y to x, and we add these complexities. Now, if we, in addition to this, apply some functions, gamma and lambda, around the first, respectively, the second term, so gamma goes around here, and lambda goes around here, then we arrive at a score like that. That's, well, A, we get to show off that we know Latin, but B, we can start to reason about what shapes can these lambdas and these gammas take, which function classes apply to. So effectively, we just assume the world to be simple. Now, if we look at AIC, the Kuijkers information criterion, you'll also know for EML, this is normally n times the logarithm of the expected error times just a number of parameters. We can change this very simply to our formulation. So effectively, under the simplicity assumption, we can use AIC-based regularization and tell cause from effect. Done. We can also use BIC. BIC is typically a bit better. It's a bit more conservative, needs a bit more data, but it's a bit better in measuring complexities. There again, this takes the shape n log A, okay, fine, and then, well, k over 2 times log n. This is still a monotonic transformation of the number of parameters. Done, right? No problem. So both AIC and BIC work just like that. Now, both of those, AIC and BIC, are from an information theoretic perspective. If you count, so they measure in something like, comes close to bits. But if you look at it from an MDL perspective, they use either too few or too many bits. These encodings are sloppy. And this is what we then called our method, right? So slope you have seen, this is sloppy. I'm happy that the reviewers didn't say, okay, well, if the method is called sloppy, I don't trust this paper, right? This was accepted in one go. So that was good. This is sloppy. So what is the general idea? Choose your scoring criterion, BSc, AIC, or whatever you wish. Choose a regression algorithm to minimize S. So using cubic splines or whatever you want, right? We literally use those. You can use basis functions. Find that spline that minimizes the error in the one direction or the score in the one direction. Same thing in the other direction. This is really just flop, flop. And then, well, choose the one with the smaller score. That's your causal direction. Easy peasy. We can also, going back to the confidence score, this decision rate plot, right, that we saw. If we now look what is the difference in the score in x to y versus y to x. How many bits difference is this? This gives us a way to determine how certain are we, right? If there's 0-bit difference, well, we don't know. If there's 50 billion bits difference, okay, then we're pretty certain. We transform this into a confidence score just by normalizing it. No magic here, but that gives you a way to order your decisions and to also see, okay, does this now do something? This is the radar plot you just saw for slope. In comparison, we have Recit, QCCD, and ICSI. So, I mean, Recit and ICSI were then pretty decent competitors on, actually, no, Recit was pretty decent on Tübingen, ICSI not. ICSI is information geometry-based causal inference. It's a nice paper, but interestingly, this one works very well on the simulated data sets, but quite badly on the real data. Recit, well, has a very different shape than we do, right? I mean, we still beat it quite badly on the real-world data. QCCD is quantile-based causal discovery in this case. This is the method that Natasha proposed. Very nice method. Doesn't have identifiability, doesn't have like robust guarantees. But that's not what we're here for. We're looking at slope. And if we now plug in a new score, then we arrive at this. So sometimes it helps to well, revisit the problem, look at the theory and see what you can do. I'm still super amazed with both slope and sloppy. As you can see, I mean, sloppy does slightly less well on the Tübingen data set, on the real world, but I can live with that. But I'm super amazed by simply doing regression in the one direction, other direction, you can tell cause from effect. Feels like such a simple idea. And why did we have to wait till, I think, sloppy was 2019, I think. I mean, it feels a bit weird, right? But why didn't people do this earlier? I don't know. Good. So let's walk through the overview. Slope, then it looks like this, f of x, noise separately. What assumptions do we have? We have the causal Markov relation, faithfulness, sufficiency, meaning the guarantees we had was, well, identifiability up to Markov equivalence. Effectively, we can't point out directions, even though we did in practice, but not guaranteeable. If we add the low noise assumption, like we then also plug in to from sloppy, then we actually do get identifiability of causal directions. Right? So the low noise essentially, oops, where are we? Over here. Then we get identifiability. We didn't look into it, but we can probably also do this for slope. Just have to use a more BIC-like score than the MDL score, so a more sloppy score, which this is the weird thing. Sometimes the sloppier score works better in theory, but the more finely grained works better in practice. But yeah, then you don't have guarantees anymore. So, okay, so this is 2019. Then what we also did, this is then in 2022. This was Sasha. I mean, after taking EML, he heard me talking about heteroscedasticity. And then he came to my office like, okay, well, can't we do causal inference under heteroscedastic noise? Like, well, no. I mean, so far all the theory says no. Okay, but can we try? And well, yeah, this is called HECI or heteroscedastic noise-based causal inference. And effectively what we do there, we take the presumed cause and we bin it into independent bins. And for each of those bins, we learn a separate regressor. Effectively, we factorize, you could say, our score into these bins, just add them up. We also do this for the anti-causal direction. And the key idea being is that even if you have heteroscedastic noise, let's say it's a plume, right? I mean, it starts small and becomes big. Then by just binning it in fine enough bins, and in the limit we have infinite data, so we can do this. Then in each of those bins, well, the independent noise assumption holds well enough. So this is effectively the trick that we use. And in what we show in the papers that in the anti-causal direction, it is impossible to get this independence, even under super fine-grained binning. HECI works very well. And it kicked off a whole line of research into heteroscedastic-based noise, but we left it for what it was because we had our portion. Now, the methods we've seen so far, both the A&M-based methods and this information theory or regression-based methods, they allow us to solve this problem, right? This is what we started with. We have the skeleton and we can orient these edges. But now we can tell once and for all which are these edges, right? Good. You could say our job is done now. And we could have, perhaps we should have, I don't know. But I was still a bit unsatisfied because if we now first learn the skeleton using, well, method A with score B, and then afterwards we clean up the mess with method C with score D, who tells me that the first method actually gave me edges that the second method can orient? I mean, it feels a bit icky, right? I mean, can we do this better perhaps? And better both in one unified score and also with better results, hopefully. So what about learning a DAG? So not a PDAG, but a DAG. This is Usman. He defended his PhD a few months ago. And that was basically the, well, at least the starting point of his PhD. And this effectively what I'm going to present next is going to be his master thesis from a few years back. And then we continued working on this general line. So we take again the same ideas that we just explored, but now we're just going to put them a bit on steroids. We take again MDL, but what we do is that we now are going to store the full SCM, structural causal model. The model is really the set of functions. And you remember from the first causality lecture, if I give you the set of functions, you get the DAG, right? And from the DAG, you can't really get the function. So we focus here on the functions. And the L of x given M, where x is now the data in general, this is the number of bits needed, again, the regression error, you could say, after the model has explained all the regularities, right? Good. And we want to minimize this thing. Well, these two parts are already a bit difficult to define, right? We saw two examples just ago. But now by minimizing overall DAGs, we have a problem because DAG search is NP hard. So meh, right? This is what Guess sidestepped by searching over Markov equivalence classes. And that pulls it into the realm of doability. But that's exactly what we want to avoid, right? Getting max. So, okay, NP. So, we need to do something different. What do? We start effectively, you will recognize here, we start with, well, this is sloppy, but at the same time, you will notice that here there's all of a sudden 3 parents. And in sloppy, there was just 1. We just had x to y or y to x, right? But now we have 3. And you could say this was the key point of Usman's master thesis, but going from univariate, or bivariate if you wish, regression to multivariate regression, such that we learn this function not just over y, but really over the parents from y, or not just over x, but really over the set of parents. So moving from a single spline, we had to move to, well, multivariate adaptive regression splines. Very nice in theory. In practice, they're a bit hairy, but we could have also plugged in, let's say, Gaussian processes, but you need some regression method that can take multiple parents. We use multivariate regression splines, which effectively is sort of a snake. It's a set of linear functions. And for each of these linear pieces, we need to specify what is the direction of the vector. That's the number of bits. So the more of these hinges you need, this is where these pieces connect. Well, there you are. So that's basically the number of bits really on the error side. Same assumptions as sloppy. And we can show that actually this allows us to identify full causal DAGs. It just carries over. The moment you can orient the individual edges, then, well, with the correct regressor, you can scale this up. So, okay, well, we're done. Except that we still need an algorithm to find these DAGs, right? How do we do this? We came up with this algorithm. We start with an empty graph. Essentially, we take, well, a greedy approach, following some insights from Guess, but not fully. What we do is we consider in the forward pass adding every individual edge to the current model. So here an edge from V to W would give us I think a gain of 90 bits, but I always forget if I now write minus or plus for the gain. So there's 90 bits difference. If we add instead this one, it would be 40 bits, and so on and so forth. We get essentially over, if we just do the pairwise computation, we need to do this for every direction, of course, right? So here we see this is 90, this is minus 11. I think 90 is really the gain. So over this, we take the best one, which is, well, 90. We add this edge to our model. Great. So we do next an update step, because V to W explains already some parts of W. So the edge that we used to have from X to W, well, that was explaining everything from scratch. So we need to upload. And you will now see that this goes from -2 goes to -12. Z this is, let's say, -17, but y to w goes from 5 to 35. All of a sudden, y can explain w much better. So that is definitely something we would like to have on board. We keep on taking greedily the best edge from the entire edge set until we can't gain any bits anymore. Then we stop. In this case, this is the set of edges that we have. Just like what we saw with guess, we need, well, we have to, we can make the error of adding a shortcut, right? So we need to have a backward pass to remove edges. So in a backward pass, we reconsider every edge individually. So here, removing this one would save 19 bits. This would cost 10 bits. This would cost 15 bits, and so on and so forth. We remove that edge or those edges that cost bits until we can't remove anything anymore, and there we are. That's the algorithm. That is globe. You could, in practice, so in theory, it's not necessary in the limit, but you could add another forward pass and then a backward pass and a forward pass and a backward pass. But there's one detail that I swipe under the carpet. What we do during the search is that for every edge that we add to a node that already has either an incoming or an outgoing edge, so let's say I just added this one, then it might be that this edge now explains part of y that previously Z was trying to explain. But now that we finally see, the light, let's flip this edge around. So we also consider edge reversals. So it's a greedy grow with reversals and shrink with reversals, and then we add something. But otherwise the slides become a bit too complicated. Now, globe is effectively tree search. And we can prove that if the true generating mechanism is a tree, and our modeling assumptions are being met, right? I mean, that's a low noise and whatnot, then actually we can retrieve the true graph with guarantee. That's neat. Empirically, however, globe kind of rocks. I mean, it is one of the easiest and best algorithms currently out there. Let me show you, I mean, I don't really like to bombard plots on you. This is on synthetic data. SHD is a structural Hamming distance. Effectively, you take the true graph, the discovered graph, you just see, okay, how many edges are added wrongly, how many edges are well, missed, also wrongly, of course. And how do you see? Green is globe. Lingam is this linear non-Gaussian, right? I mean, this data is, of course, not linear and non-Gaussian because that doesn't exist. Resit, that's the orange line. You see that's, well, it's a reasonable competitor, but not super great. This is the PC algorithm that you know and love with the Hilbert-Schmidt independence criterion as the independence test. And the purple line is the generalized version of guess, generalized in the sense that it can also take non-equivalent scores. But that's not so important right now. And as you can see, for different sizes of parent sets, so for larger and larger graphs, I mean, globe, well, scales quite well. Not perfect, but quite good. One of the interesting questions could be to look into, can we marry globe and guess? And, well, formally it requires then this equivalence, an equivalence-based score, which we do not have, but this generalized guess should be able to take the globe score. There we had a bachelor student, very bright one, who came up with a sampling-based algorithm that can marry the two. It has a quite horrible runtime in practice, but it does really well. So there is definitely something there, but, well, it's still a tough nut to crack. So we can now learn a causal DAG from scratch. And actually better than, well, first using PC or guess and then orienting it, we can find it in one go. Good. Let's take a 5-minute break or 10-minute break. Let's take a 10-minute break. And then I continue with the second part. Yeah, good. Oops, no, what you're doing. You off. Allow you a bit of light to wake up again. There we are again. Contrast good enough? Or should I make it even darker? Well, I think the sun is disappearing, so that's doing it. Good. Okay, so we can now learn a causal DAG. Isn't that fantastic? That makes you question, like, can we do more, right? Because so far, we've been assuming that we were given one data set. And in practice, that is not really the case. Often you have multiple data sets, either from different locations, let's say different hospitals, or you've done some interventional experiment and you know that, well, you got the purple pill, you got the yellow one, and so on and so forth, right? And that's yeah, I should not put all of this on one big heap. I should treat these differently, and perhaps not just by simply adding a column with the color of the pill that you might have gotten, right? And then seeing what happens, although theoretically that also gives you quite a bit. Better look at it. We can now discover a causal DAG, but can we discover interventions? Can we discover from some data that certain environments may have been subject to a hard or a soft intervention? Or essentially, if we were to throw all data on one big heap, well, we might find either a supergraph of this or a subgraph of this, because the method can't really decide if it's so there might be only a few people who got the gold covered pill, right? Because of gold expensive and whatnot. So that was the idea that we set on afterwards with Usman. And that arrived in the end at Orion. And Orion, you could say, is just globe. I mean, there is quite some details below the hood, of course, but I'm going to, for you, pretend it's just globe. And what we now have is that we have, in this case, 3 data sets. We can have arbitrarily many. We have our empty graph overall. And as you can tell, we have, well, local graphs for each of the data sets. And what do? We greedily try to add an edge to the global graph. And we see how many bits does this gain or cost at the local graphs. So this one, V2W, the top database likes it. If we add this model, we gain 43 bits. The second one likes it even better, 53 bits gain. And the other one doesn't like it, 0 bits. Okay, so it's not like it's horrible, right? But I mean, it does not add anything. So we can just as well not have it. Effectively, this allows us to contemplate the following set of interventions. That on the first one, there's no intervention compared to, well, the global graph to the local one that is being liked most. Second one, same thing. And the last one, adding the edge V to W, no, not a good idea, right? It could have been like a negative gain. Basically, we can say this is a hard intervention because all incoming edges to W are being removed, right? This is one way how to model that graph from this one. But it already gives you an intuition for how Orion works under the hood. So we're not just modeling a set of functions like we did with Globe. We're not just doing this for one graph, we're actually doing this, the functions themselves for each of the graphs. But we're explaining the local graphs, like is there an edge, yes or no, by having a global one on which we intervene. So from this one, we arrive at that one by doing a hard intervention. This intervention set also costs bits, obviously. Yes.
Is the global graph frame of all 3 data sets combined?
Yes, yes. So the next step would be, so overall, what we now see for this particular edge, that by having now this one, so the edge edit in the global one, not having it in the orange one, having to encode this, right? How many bits do we now gain? Overall, this costs us 6 bits. Okay, we don't like it. Oh, actually, no, this costs 6 bits. It gains 90 bits. This is the dance that we're doing here. So, okay, we will keep it for now. Next, we could consider adding the V to W as the other candidate, right? There is one data set that likes it, the top one, the other 2 don't like it. And we have again some cost here, right? We do this again for every edge, and look and behold, we have exactly the same graphs that we have the globe, because I just was lazy and I used the same numbers, but the globe graph was just the Orion graph minus the interventions. So otherwise, the algorithm now works exactly the same way. We take that edge in this graph that gives us the highest gain, that is that one, with this intervention set, right? So this graph and intervention set. And we update, just like we did previously. Oh, sorry. We update those. You've already seen that, so hence I removed it in the animation. And I just greedily loop through. I again also reconsider like flipping edges, but not so important. In the end, right before doing the backward pass, or maybe this is already after the backward pass, I think, we arrive at this graph over here and this intervention set. So there is a soft intervention on, so that is this edge here being missing, right? So removing this edge is a soft intervention. Oh wait, on Y, sorry. Where are we? Ah, this is for blue. Okay, I should have colored this in blue, sorry. This is this edge missing, soft intervention on Y. Here we have a soft intervention on X, that is this edge missing. And for the orange one over here, we have a hard intervention on W because all edges are removed, and a soft intervention on X, which is this edge removed, this one over here, but not that. So hence it's a soft intervention. Effectively, by using exactly the same machinery as you've seen before, regularized regression, but now the regularization takes also into account the graph and arriving at the local graphs from there using this penalty, we can show that we can actually identify, meaning if we have infinitely much data for each of the data sets, we can actually tell, has an intervention happened, yes or no? And on which variables has this happened? This is pretty neat, because the only thing I now need you to give me is just multiple environments. If no interventions happened, well, I will be more robust in finding the overall graph. If interventions happened, well, unless in every environment all the edges have been completely mixed up, then of course we're screwed, because there needs to be one common graph on which all these interventions have happened. But otherwise, I can much more robustly do causal discovery. This is again an idea where we're sort of in the rung 2.5, right? We do the modeling parametrically, we're reasoning about the SEM, we're reasoning about interventions, hard do interventions, soft interventions removing individual edges, which is really a rung 2 type of operation. Does this work? Yes. These graphs are not necessarily the easiest to read. Whoops, back. This is Orion, where this is a plot where this is the SHD. You already know the SHD. SID is the structural intervention distance, where we measure if I would wiggle a certain variable, and I do this both in the graph that you gave me, and I do this in the graph that, well, the true graph, do I see an effect on the same set of nodes? So I look at X, I try to wiggle Y, right? Do I see an effect in your graph? Do I see an effect in the true graph, right? So it could be direct or indirect, doesn't really matter. Or if there's no connection between the two, well, and there should be, then you get a penalty point. So SID is a more causal interpretation of the SHD. Origin is better, well, Orion is better on, this is gene expression data, and here as well. These bands that you see, and these intervals, it's because those methods, they don't give a fully oriented DAG, they give a PDAG. So we computed it both for the best possible orientation and the worst possible orientation. And well, the true one that you would arrive with any of our methods or any other orientation method would be somewhere in the middle. So in theory, CD0 can beat us on at least SID, sorry. But in practice, it will probably not. Good. So much for causal discovery. And actually already, like, we went a bit beyond normal causal discovery because we can now discover DAGs. We can actually do this from multiple data sets while we're also discovering interventions already. All with the idea, let's compress the data best. It's simple and, well, straightforward. Now the next 15 minutes, and then we're going to call it a day. I want to talk about chocolate. Does chocolate consumption cause Nobel Prizes? Or doesn't it? Well, this is data, I think, from 2005. Originally meant as a joke paper, but then actually, well, the joke turned out to be much more complicated than people thought. So I only have currently this slide, but I can reason a little bit about it. So what we have here on the y-axis is the chocolate consumption, kilos per year per capita. And on the y-axis, we have the Nobel Prize laureates per million in population. And as you can tell from the way that this is plotted for these countries, well, it's not random, right? So, which raises the question, is it now that people eat more chocolate that then they become smarter? Is it because people, well, Nobel Prizes, people are super happy, that leads to giant chocolate fests, right, where people eat a lot of chocolate? Or, yeah, what is it? Now, the dependency between these variables in the R is 0.791, which has a p-value, if you assume just uniform noise, is minute. So this dependency is really significant, right? What is going on here? Or what could be going on? Max, you're allowed to speak.
I would say there's another.
There's another variable. Which variable? Hello, Prakar. I hope that we're still streaming. I'll share my screen again. I'm not a big fan of this room, but okay. But yeah, even if you condition on all relevant variables, there's still something left. So there is truth to this question, right? Let's ignore this for now. If we were to throw this data onto the bivariate causal discovery methods that we've seen before, they will say something, right? I mean, is this truly an A&M? No, because it looks kind of linearish and not. But it will give you some direction. But if Max's intuition is correct, then this direction will be nonsense. If we were to have some data on which we do our causal discovery in general, it will at the very least find an edge between those, which is also not what we would like to find, right? Effectively, what we're looking into is that the sufficiency assumption is being broken. Effectively, what we postulate here, there is actually a hidden confounder, let's say GDP, economic wealth, education, whatnot, right? That actually causes, well, let's make this chocolate, and this is Nobel Prizes, right? But by not measuring this, we will see in the data an edge. Whoops. PowerPoint and animations. But the whole point of this where conditional independence tests, what they rely on, this explaining away, this filtering out, is that if we see a dependency between X and Y, and we can make it independent, we can find a confounder in the data Z that explains it away, then we're here, then we know that there's no edge between them. Otherwise, well, it's X to Y or Y to X, right? I didn't, right? Now, the problem is, of course, that it's impossible to measure everything relevant. Sometimes we could, but we forgot about it. Sometimes we could, but we don't know about it. And sometimes we just simply can't. Biology is a great example. Also with the interventions, right? I mean, if you know, let's say the golden pill or whatever, right? I mean, that changes some the ways that's your gene regulatory network or system, right? It changes certain things. It is not going to be a surgical change, just this. I mean, everything is connected. So all of a sudden, many things change, and yeah, what is it now, right? There's no way we can measure the expression of every possible gene, of every possible protein, in every possible cell, under every possible time point. Things will be confounded just naturally. So hence the explaining away, let's assume that we have measured everything, it's not very realistic. But it raises the question that, hey, well, if we haven't measured everything relevant, but we do know that Reichenbach allows us to explain things, why don't we just conjure it up? Why don't we think of a Z hat, right? That's exactly what you just did. Effectively, I guess that in your head, right? I was not there, but meaning in your head, like, okay, I see these variables. Maybe you looked at the names of the countries, right? I mean, okay, wait a second, or you have some connection in your head, like, okay, well, Nobel Prize is probably education, and so on and so forth. You were reasoning a bit like that, right? I suppose. So you were looking for a Z hat. Okay, well, you were doing this with world knowledge, right? With a model of the world in mind. If we just would have given you the numbers without telling you what is the meaning of column X and top column Y, life would have been a little bit more difficult, right? So let's play it now in that realm. What is wrong with this picture? What is the problem? So I give you the one column of the number of Nobel Prizes, other column chocolate consumption per capita per year, right? And now the question is there a confounder? Let's find a confounder Z hat that makes these two columns independent. That's what we want to do, right? Any intuition?
Maybe more than 1/7.
How many more?
Any more?
Infinitely.
Yeah.
Infinitely. That is one thing. Can anybody come up with a trivial example? So not just one out of infinite arbitrarily, but really, what is a trivial example? Why is this searching for a Z hat that makes X and Y conditionally independent? Why is this doomed to fail? Max?
I think we're just taking the example.
Exactly. It's too easy. Just by taking X or Y, I'll give you that. That was not in the slide, right? That already works. And even if you take then, well, a minute jitter of X or Y, you're also there. And there is a vast universe. It's too easy, right? So this doesn't work. This is also why for a long time people just ignored this problem. Like we can't do anything, right? I mean, that's a bit like with orienting these edges. Now, what we can do, we in this room, we can start to reason about confounding in terms of Kolmogorov complexity, in terms of complexity in general. And confounding can look like this. It's not necessarily the one and only model, right? But what do we have here? I have here a joint distribution over X, the observed variables, and Z, the unobserved confounders. So some joint distribution, right? I mean, that's so both the things we measured and we didn't. Now, we can split this complexity into two parts, namely that of just the confounders. And what we have here, we have the sum of each of the confounders, the complexity of their distribution. Note that these are all marginal. I'm making here the explicit assumption these confounders are independent of each other. Is this realistic? No, but need to do something, right? I mean, so let's start with making them cleanly independent. The moment you make them dependent, then we need to make other very strict assumptions on how are they allowed to be dependent, which shapes can they take, otherwise you have identified issues. Okay, so these are independent, and what we now have here on the left-hand side, we have the Kolmogorov complexity of the distribution, conditional distribution of a variable xi, given the parents, and I have this prime because this prime now includes also whichever are the relevant hidden confounders. the idea being is that if I give you now data over X, the simplest way to describe it is actually to think about what would the Z be, what would it look like? And I can now start to think about two scenarios. One where let's start here. One where I encode, so these are the observed variables. Actually, no, yeah, okay, this slide I'm not entirely happy with. I can do this. I can also put my hand over Z there. So I just force you to describe the data as it is. That's the one scenario. It takes a certain number of bits. And I also allow you to encode the data with this Z, but you will have to encode this distribution of Z. So it's not that I give you something for free, right? But if by reasoning, GDP, economic development, the whole picture becomes easier, literally simpler to describe, then you will do so. Same thing if you just get the numbers. Yes.
I'm just wondering, because we said we are assuming here that the data variables are independent.
Yes.
I mean, if we're choosing them.
Yes.
And we not always assume this because
Yes.
there would be two independent variables. We
Sure.
justify a new one that is basically the join.
Yeah, yes and no, yes and no. So this is one of those catch-22 type situations. We explicitly assume them to be independent, and by doing so, we can only, well, solve. I mean, identifiability here is based on Kolmogorov again impossible, but we can only deal with situations where it is truly independent. If these sets are truly dependent, then we can sort of go one step up all the way to the exogenous variables, but I mean, we would be combining different Zs into one independent Z, and that is then not the true model. So that may not have the true lowest Kolmogorov complexity. So you see where it's really one of those rabbit hole type of things. Okay. But the general idea, explain the data as is, and explain the data with, well, something in addition that you can make up yourself, but you have to pay for it yourself as well. But if that is easier, then you go for that. Okay, how can we now get those distributions? Because the left-hand side is reasonably straightforward based on what we've seen before, right? But finding these Zs, I mean, yeah, how would you do this? Well, I already showed you, flashcard you this slide. How do we get this? If we use probabilistic PCA, so you know PCA from earlier classes, I suppose, right? There's also a probabilistic interpretation that doesn't give you just, I mean, the principal components, but actually a distribution over them. It's convenient for the score that we derive at. Effectively, what it does is, let me see, you start with modeling the data as it is, right? So in this case, I mean, let's say this is the true target, I mean, that we're interested in. Everything is just on the observed variables. We're trying to fit a latent model by squishing as much of the information that is shared between all the axes into the Zs. We allow a certain budget. And in the end, after fitting, what we try to do is actually model the data like this. So we force all the x's to be conditionally independent given the Zs, right? So Z is now going to take all the information that is relevant in X and anything dependent. So if there's anything dependent in X, it will arrive in Z. You can also see this like with PCA, right? I mean, if you have two completely independent variables, then yeah, well, the principal component is going to be useless. If you have something that is linearly dependent, the first principal component is going to be super helpful, right? Principal component is basically the Z. Okay, so this gives us a way to get our hands on PZ. And the moment we have PZ, then well, the conditional distributions is again this sort of like regression error type of thing we've been talking about before. Now, how the score works exactly, I'm going to swipe again under the carpet. If you really want to see this, I mean, and I can lecture about this for quite a while. But it's not really the point. The point is really we try to extract information common between these axes. We can measure the complexity of those distributions and how well they explain the data. And we can also compare the other situation where we don't extract any information to Z, there is no Z, and we just force the model to explain the data as is. If two numbers of bits, we take the one that is smaller. The difference between the two is again how certain we are that something is confounded, yes or no, right? Under this model. Now, again, the caveats, we assume the Z's to be independent. It's probabilistic PCA, so the dependencies from Z to X are supposed to be linear, right? Not all the connections, but those connections are supposed to be linear. So this is a bit of a limited setup. Does it work? Remarkably. So this is genetic gene regulation data. So absolutely no way that our assumptions hold, right? What we do, decision rate. So for those pairs of genes where we know, of course, in ground truth, if they're confounded, yes or no, we give the X and Y, we don't tell it that there's a Z. We allow our method to look at this, determine the cost with and without confounding, and we order them by the difference between them, right? So this is how the decision rate. So here are the ones where there's the biggest difference, here there's no difference. Between these dotted red lines, this is again the coin flip. So between the dotted red lines, insignificant. The fact that linear, so probabilistic PCA, this very simple idea, actually stays quite a bit above the significance threshold. It's not as impressive as the slope line, right? But still, we can actually determine if something is confounded with much better accuracy than a coin flip. Now, if we look here on the right-hand side, we have the confidences. So these are the normalized differences between, well, yes confounded, no confounded. And as you can see, there's a big similarity between the left and the right graph. And that's actually the result that makes me the happiest. Because if on the right-hand side, I mean, I can easily set a threshold, right? I mean, okay, I'm not going to listen to my method unless it's at least so-and-so confident. And that correlates 1-to-1 to an accuracy. So the tail, so if you really ask for the accuracy over everything, then, well, we're just above or just at insignificance. However, I have the option of saying, you know what, I'm just going to take the top 25, and at top 25, I'm at a 65% accuracy. Or I can push it further with a method that is so ridiculously simple and that you can so easily scale up by not using a probabilistic PCA, but using like a deep PCA or whatever, it's some deep latent factor model. There's so many ways that you can improve this that if this already works, this is nice. Okay. We can also do this for real data. Real data, so Dominic looked into a setup where he has a TV producing, well, noise. It's just background signal, right? Then he pointed a webcam at the TV, and he takes the feed from the webcam and a low resolution image on his laptop, right? Then he has a light sensor measuring the intensity of what is shown on the screen. He's a physicist, so this is he loves building these contraptions. But now we need a confounder, right? Because right now it's still all causal. The confounder is this. We have an LED in front of the TV screen, and we have an LED in front of the light sensor, which is controlled by a microcontroller that is basically variable Z, right? So if Z is high, then both images get oversteered, right? If it's low, then okay. This is the general idea. Now, by changing the intensity of Z, we can change the confoundedness of this setup. And the strength of confounding goes from 0 to 1. The dashed line is just the 0 line, and the dots are the confidences of our method. And the red line is just if we do regression over that. And as you can see, I mean, it's again not perfect, but the method is ridiculously simple. And it correlates very well with the strength of confounding. So it's not just can it tell confounded yes, no, but also we have a signal of how strongly confounded it is. This is neat. This is neat. So how about the chocolate? Well, with a very low confidence. So therewith, I would say, let's not trust the outcome, but our method says, yes, this is confounded. So that is neat. That is neat. Good. Okay, it is 1:45 or 12 to noon. You could ask, what about causal discovery under confounding? That's what we're going to discuss then next week. Or the week after. I think next week there's also no lecture at the top of my head because big evaluation, everybody's busy here. So then the week after. Good. Okay, so just to quickly recap, using the idea of simplicity, formulating it in terms of Kolmogorov, respectively MDL, allows you to solve problems that otherwise stumped people for a very long time. Orienting individual edges without making super strict assumptions about the relationship in the sense of additive noise. it allows us to do causal discovery, really getting a DAG out of it. And it allows us to discovering interventions. And it allows us to tell if nodes are confounded, yes or no, which is pretty neat already. Next lecture, we're going to push this a little bit further, this general idea, moving also a bit away from pure causality. Causality is going to be still our friend, but we're going to be looking into, can we do causal discovery under hidden confounding? That's one step. And the other step we're going to be looking into, suppose that we now have multiple data sets, and we would like to find a robust model that works well for all of these environments. How can we do so? And then we're going to tap into some causal insights to basically achieve a better version of empirical risk minimization, if you wish. So that's the plan, and looking forward to seeing you then again. So thank you. Bye-bye.